Nice. Okay, so today we're going to be talking about it's an extension of what we did last Wednesday, right, when we talked about conservation of linear momentum. The book refers to this as conservation of the moment of momentum. More commonly, it's referred to as angular momentum, right? So just as in linear momentum, we have Newton's second law, right? Forces is equal to the rate of change of linear momentum. We also have the angular equivalent, where the sum of torques on a system is equal to the rate of change of the angular momentum. So what we're going to be doing today is deriving the moment of momentum equation, as the book calls it, or what I call the angular momentum equation. It's a pretty short derivation. By necessity, we're going to be skipping some details, so this is definitely one where the application is going to be a whole lot easier for you. You're less likely to make mistakes if you do the reading. Okay? This is this chapter in particular, chapter 5. And this topic in particular is one where we just can't cover all the material here in the room. We're going to be learning how to calculate the torque on a system caused by moving fluid. So this little prompt that I gave you here with this right turn elbow. And then we're going to figure out how to calculate the torque and the power of a shaft for rotating machinery, like fans, blowers, pumps, etc. This third point is where the angular momentum equation really becomes a powerful tool. Okay, so this little exercise here, right? Given some mass flow rate m dot through a right angle turn, okay, can we figure out at least the direction of the horizontal force, vertical force? Horizontal force is going to be the left to the right. Think back to, there we go. Think back to Wednesday, all right, where we talked about the force on a control volume, or the contents of a control volume, right, is basically, if it's steady flow, which in this case we'll assume it's steady, it's basically the difference between the momentum going into a system in each direction and the momentum coming out of the system. So, for example, we would say that the force in X, here, the horizontal force, is going to be equal to m dot in times u in. This has a negative sign because it's flow in, plus m dot out, u out, right? U being the x component of the velocity. All right. M dot out. Well, we've already established, right, if it's one inlet, one outlet, then m dot in is equal to m dot out. It's just equal to m dot. So we'll go ahead and say this is equal to m dot u out minus u in. So what this is telling us, right, is, as I said before, it's if you think of what I tried to point out on Wednesday, you think about the velocities that are inside of your Reynolds transport theorem, right? We're thinking of those as the amount, they're velocities, but they're really the amount of momentum per unit mass. Okay, so you've got mass flow rate and a difference in momentum per unit mass. So this tells you the difference in momentum going out of the system from that going into the system in the x direction. Okay, at the inlet, our u inlet is v1. At the outlet, there's no x component, right? So this turns into m dot 0 minus v1. Okay. So this suggests that the force that we're getting here, right, the force on the control volume, or the contents of the control volume, is directed to the left, right? It's negative. That's the force on the fluid flowing through, right? That's the contents of the control volume. What's producing that force in this case? The walls of the pipe. Okay, so there's a reaction force on the pipe that's equal and opposite. So if this pipe were, bolted to a wall or hung on a pipe hanger, the idea is then that the reaction force on pipe would be m dot v1 directed to the right. Okay. Similar thing for the y component. We'd end up with m dot v out minus v in. That's the y components of the velocities. Y component of the velocity going in, 0. Y component of the velocity coming out is v2. Plus y equal to m dot. Or sorry, this would be negative v2 because it's directed downward. Negative m dot v2. Okay, so once again, this implies the force on the water flowing through the pipe is directed downward. That's what causes it to turn that corner. Right? This is a thought process you want to become comfortable with, is the idea that these forces, right, the sum of the forces on the system, not necessarily whatever you're drawing a picture of. So the reaction force on the pipe from the water as it goes through that turn. Reaction pipe ends up being m dot v2 directed upward. Okay. So what would be the moment about 0? Okay, or about this point O. That is, if we were to attach, if we were to, somehow anchor this pipe to a wall or to the floor, the question is, what moment would be put on that anchor point? Well, at this point, it's just a matter of a free body diagram, right? Where you would say, if we've got our pipe, we've already established that there's a reaction force occurring along this line of action, okay, and a reaction force occurring on this line of action. And if this is point O, then just by inspection we can see that the forces on the pipe due to the water flowing through it would cause a counterclockwise moment. Right? Okay, so this is what we're going to be focusing on today. It's this idea of formalizing this sort of this intuitive sense of, okay, we know if there's force here, you get a moment. We're going to be formalizing this so it doesn't get a whole lot more formal. Basically, it's this: find moment arms, find forces. But we're going to be taking it to rotating machinery where things get a little bit more complicated. Okay, so the angular momentum equation, or the brief derivation here, we'll go ahead and commence. It's basically that, right, if you've got some particle, Newton's second law says force on that particle, we'll go ahead and say just F sub P is equal to, right, time rate of change of the momentum of that particle. Okay, at the same time, the location of that particle can be written in terms of any inertial reference frame. Remember, an inertial reference frame is just a reference frame or a coordinate system that is not accelerating. So if we draw a three-dimensional coordinate system, we could say we've got x, y, z. Maybe our little particle is out here. Okay, so this is our small volume. And we could write its location in terms of an x component, a y component, and a z component. And we would represent that as a vector r. So xp plus ypj plus zpk. P and zp. So the reason we use this this distance vector, this location vector, is because, right, any quantity, whether it's mass, vector, or mass, velocity, force, you can get the moment of that quantity at the origin by taking the cross product of r with that quantity. So if we take the moment of both sides of this equation up here, okay, about the origin, we can write r cross af. That's the moment of the force on this particle. Okay. R cross f is equal to r crossed ddt of rho v delta v. All right. Now there's a little vector, or there's a in this case there's an identity that we can invoke that I'm going to skip over here for the sake of time, but essentially we can show that by application of the product rule from calculus, we can show that this is equal to ddt of r cross rho v delta v. In other words, we can move that r into our Lagrangian derivative. Okay, this is important because now, right, some of the moment due to a force on a particle is written in terms of the rate of change of some quantity. Okay, so we're back into conservation law territory, and this is going to head back towards our Reynolds transport theorem. So if we want, to consider all of the particles that make up a system of fluid, right? Essentially, if we wanted to sum up all of the little infinitesimal forces at the respective distances from the origin, and on the right-hand side, to sum up all of the rates of change of moment, or the moment of momentum of each of those particles, we would do that through integration, right? So integration over an entire system, right, which is just made up of many particles, gives us basically the sum of all moments on the system is equal to time rate of change, the integral over the system of r crossed v rho dv equal to, right? If we didn't want to write it as we'll go ahead and call this T, the torque on the system. So now what we're seeing is an expression saying that the sum of torques on a system, okay, sum of torques on system is equal to the time rate of change of angular momentum of the system. So we have our rotational equivalent to Newton's second law. Okay, well, just as before, right, if we pick an instant in time, we can say our system at that snapshot in time makes up the entirety of the contents of a control volume. So the sum of the torques on the system is the same thing as saying the sum of the torques on everything inside of a control volume. The torques on the system is equivalent to sum of torques on control volume contents, which begets an application of the Reynolds transport theorem. So in order to apply the Reynolds transport theorem, basically what we're doing is we're going to be writing this rate of change of some quantity of a system in terms of control volumes, control surfaces. We need to pick, once again, our little b, our intensive properties, and our big B, our extensive properties. So big B in this case, we've got d b system dt is equal to c v rho b v plus integral over cs rho b v dot n dA. So there's our Reynolds transport theorem. What are we going to plug in for big B? Match this up right here. Okay. What's our extensive property of the system? What are we trying to capture the rate of change of? This R cross V quantity, right? The moment of a velocity about an origin of our coordinate system. Okay, it's a weird concept, but just do a pattern matching here. We've got our time rate of change of something of a system. Okay, that's what's on the left-hand side of our Reynolds transport theorem. Just look at what we're capturing. So our B would be R cross V, and little b then is simply, big B is going to be R cross V times I guess in this case it would be times mass. And then little b is going to be simply R cross V, that is big B per unit mass. So plugging those in, you can write that ddt, of R cross V rho d volume of the system is equal to time rate of change over the control volume of rho R equals to V plus integral over the control surfaces of R cross V rho V dot N dA. This is equal to the sum of the torques on the control volume contents. Alright, so this here is what we refer to as the angular momentum equation, or the moment of momentum equation. Really, it looks very similar to what we've been doing with the linear momentum equation. The only exception being that we've simply put an R cross in front of everywhere that we had a velocity. Okay, everywhere that velocity was our intensive property. So just as before, we've got the time rate of change of angular momentum in system equal to the time rate of change of angular momentum of control volume contents plus net rate of efflux, remember that's the flow out, of angular momentum through the control surfaces. is equal to sum of the torques on the system / control volume contents. Okay, so in a case like the little preliminary exercise that I gave at the very beginning of the lecture, we've got something like this. Okay, flow through a pipe. In this case, you would solve it essentially in the same manner you do with the linear momentum equation. You would say, if here's O, okay, what is, right? You'd find the distance vector to the outlet, you'd find the distance vector to the inlet. From that point, you multiply those in there, and or as cross products, and what you would get is something that looks like V1, V2. Let's go ahead and say that this is X2. You'd end up with rho V1 A1 times V1 times well, it'd be Y1. That is the Y distance from the center of this inlet to our point. Which in this case is equal to 0 because the flow is in line with our point, our reference origin. Plus rho V2 A2 V2 times X2, and we need to verify that. Let's see. That would be a positive value, but that's a negative there. Right, and so our angular momentum equation would simply boil down to this. I'm skipping a bunch of the intermediate steps, but we're taking into account that we have one-dimensional flow, so this integrals just turn into, right, V1 A1 times rho, and then those cross products at the inlet and outlet, we've simply said, all right, we could use the right-hand rule. We could say that, right, V2 times R2 in this case, or R2 crossed with V2 would be, right, index finger in the direction of R2, middle finger in the direction of V2, and then your thumb is going to indicate into the page. In this case would be, would be negative, right? In other words, if this is our coordinate system, X, Y, then that cross product would have a negative sign in front of it. And so it's just, you're just plugging in one more quantity. All right, I can already tell we're almost certainly going to run out of time here. I'm going to try to spend more time on this in the next lecture probably, but we need to move on to the more important concept of rotating machinery. I'm going to try to adopt this on the fly to avoid recovering ground. But the most common application for the angular momentum equation is this idea of machines that rotate, things like sprinklers, fans, blowers. And in going over this, we are going to discuss a few simplifications that are going to that we're going to rely on whenever we're dealing with the angular momentum equation for this class. Okay, those are one-dimensional flow at inlets or outlets. Okay, that's going to simplify our integrals significantly, remember. And we can also assume that we can deal with flow that is steady. All right, these two facets here are going to make life a lot easier for us because, as I was just saying, right, if we can deal with steady flow, then that means this first quantity here goes away, okay, because it's got a ddt in front of it. If we can deal with one-dimensional flow, right, that is flow where v does not vary across an inlet or an outlet, then basically what that means is that these quantities here can be considered constants. They come outside of the integral, and that's why where we end up with much more simple expressions like this. So consider, I've got a slide here. Okay, so an example here shows a rotating sprinkler head where we've got flow entering down here, right? It moves up, out, and it gets directed outward. And we might be interested in knowing what, for example, the torque on the center spindle or the shaft of the sprinkler head is that's created by the flow being jetted out in this sort of tangential pattern. Okay. We might also be interested in knowing, what is the actual power that's being generated, mechanical power, that could be harvested from this type of device, if we wanted to treat it like some sort of turbine. So to do this, we would set up a control volume that looks like this right here. Basically, we're interested in the sprinkler head itself. We would say that we have flow coming in here, right, and exiting out. Flow coming in here and exiting out tangentially. There are a few little bits of terminology we need to get straight because we're dealing with our control volume itself doesn't move. Okay, our control volume is this disc that sits around the outside of the sprinkler head, but the sprinkler head is moving inside of it, and so there are a few definitions we need to make. For example, shown on this figure on the right, we've got this, what we're calling W. Okay, this would be defined as the relative velocity, say, between the rotating machinery and the fluid. That is, W is the fluid velocity that you would see if you were riding around on the nozzle of this sprinkler head. Okay. At the same time, the sprinkler head is rotating. Okay, it's spinning around, and so we would define another velocity, u. Right? U is the tangential velocity of the nozzle, where the vector u is equal to the distance from the origin, the point of rotation of the nozzle, times the rotational speed of the nozzle, times the unit vector in the angular direction. Okay. And then we would have v, which is the absolute velocity of the fluid that's leaving the nozzle. Okay, and the way we would get v is from this definition of, right, if w is the relative velocity, that means that, right, oops, means that w is equal to v minus the velocity of the nozzle itself. Okay, it gives us the difference between those. And so we could say, flipping that around, right, v then is equal to w plus u. Which in this particular drawing we've got here means that we would have basically we would, let me redraw this. If this is u, then this arrow here would be v. Draw that one more time over here. U and v. Okay, so we have three velocities that are really only two of them are unique, and the third one can be found from this identity between the relative velocity, the rotational velocity of a nozzle or an exiting point in a rotating machine, and the absolute velocity of the fluid. So with this in place, I'll give just a few more seconds to make sure everyone writes this down. With these definitions in place, okay, we could go ahead and write the angular momentum equation that we had before. In other words, we would say the sum of the torques is equal to time rate of change of the control volume, rho, v, r cross v, dv plus integral over the control surfaces of rho, r cross v, v dot n, dA. All right, so we said that we're going to assume it's always steady flow. So this goes to 0. And so we can split this second term into integral over, right, the inlet of rho r cross v, v dot n, dA, plus the integral over the outlet of the same integrand dot n dA, and this is where the second or this first assumption is going to help us so much. But one more simplification we can make here. If we're interested in the torque about the on the shaft, okay. The torque is a vector quantity, right? The torque, it's the cross product between a moment arm and the force. The torque along the shaft then means the component of that vector that's aligned with the axis, the longitudinal axis of our shaft. Okay, so this is basically, we seek, right, T shaft, which is, right, the total torque dot product with the z unit vector. Okay, so we're looking for the component of the shaft torque that lies along the shaft. That's all I'm saying here. So if we look at this, okay, at the inlet of our sprinkler section, right? We've got our control volume. The flow is coming like this. I want this to be blue. The flow is coming up like this, and right, exiting. At the inlet of our control volume, basically right here, what direction is the velocity going in? Okay? It's parallel with the shaft, right? The cross product with any vector is going to be perpendicular with respect to both those vectors, right? So this means that R cross V is going to be perpendicular to the shaft, right? We can just tell that by inspection because V is parallel to the shaft. And so if we're interested in the component of the resulting torque that lies along the shaft, the issue is if this is perpendicular to the shaft, then as soon as you take the dot product with the unit vector along the shaft, it's going to go to 0. In more plain English terms, what this is saying is that flow, right, along the shaft isn't going to create any sort of rotational moment, which is something that should be fairly intuitive to think about, but this is the mathematical expression of that. So what that allows us to do here is say, all right, the inlet in this case does not contribute any moment toward the torque around the shaft. So we're left with only the flow out through the nozzles of the sprinkler. All right, and now this is where, I should say, this is where this 1D flow assumption is going to come in so handy, because we've said that this is constant, right? All of these quantities are going to be constant around this control surface that we've set up at the outside of the nozzles. As our control surface looks like, right, this sort of this strip that is has a constant radius of R2. And so this whole quantity, right, this integral, we're going to invoke this 1D assumption. And we're going to assume, because we're working with water, that rho is equal to a constant. This is going to end up being R cross V, okay, R2 V2 times rho V dot N times the surface area out, okay. Well, V dot N times A out, especially times rho, right? This collection of terms right here, if we multiply it together, what do we get? Mass flow rate. This turns into m dot. Okay. So we're talking about mass flow rate, and just as a comprehension check, mass flow rate, right? R cross V, we already said earlier, is the angular momentum per unit mass. So this should represent the amount of angular momentum leaving the control volume, okay, through this outlet. So the next part is where things get a little bit, it takes a little bit more intuition. Now, essentially, we've determined that up to this point it remains pretty general. But if we want to simplify it any further, right, we can say this R2 cross V2, we could write this as, right, R2 times V theta 2, that is the tangential component of V. So if this is our control surface, right, we've got R2. This is V2. This is made up of V theta 2, oops, and the radial component, okay. Which means this needs to have a plus or minus sign in front of it. And the plus or minus sign is going to be dictated by the right-hand rule. In other words, you need to look at the direction of V, and you need to look at the range vector R and determine whether or not that cross product is going to be positive or negative. For example, what we're showing right here, okay, this little sketch that I made, would it be positive or negative? thumb is pointing into the page, okay? Generally, the convention here is x, y. That means that counterclockwise is positive. So if this moment that we're creating is clockwise, it needs to be negative. This quantity here would be a -1. What if we had something that looked like this? This time it's going to be positive, right? But in a case like this, now this term, right, would be negative. So there are a lot of things to keep track of here. Essentially, here, let me go ahead and write this one more time, times rho plus or minus m dot. Oops. Okay. The plus or minus sign on this m dot is going to be determined from, right, the sign of v dot n. So if you look at your normal vector, the first case we had here, right, the component of v that is radial is pointed in the same direction as a normal vector, so that's positive. That means it's an outlet. In the second case, that v dot n term would be negative, indicating it's an inlet. And then the plus minus sign here, determined from the right-hand rule. Okay, so that's actually almost complete. I do have an example that I'll upload, and we'll finish up what we didn't get to when we talk about this on Wednesday.